Today's session is a very, very exciting one, and it's one that I do not wish for anyone to miss out on. As you can already see, today's session is going to be focused on regression algorithms, and it's not just going to be a surface learning. We're going to be having a deep dive, and we have somebody very amazing who's going to be leading the session today in the person of Ridwan Amure. Now, I'm just going to give a brief about who Ridwan is. Let's see. Okay, so Ridwan is a PhD candidate at the University of Arkansas in Little Rock, United States, where he focuses on using mathematical modeling, graph theory, machine learning, and natural language processing to identify deviant socio-technical behavior on social media. His machine learning solutions have seen him help companies solve crucial decision-making processes by building trusted predictive models. Ladies and gentlemen of the AI Summer of Code 2.0, please put your hands together for this very amazing facilitator who's going to be handling the session today. I will be taking us on a very deep dive, right? Please put your hands together for Ridwan Amure, who is a machine learning researcher at the University of Arkansas. And yes, absolutely. So Ridwan was also on the faculty in the previous cohort or in the previous edition of the AI Summer of Code. And trust me, for persons who were in the past edition, it was a very exciting. You can see how he's smiling in his pictures, right? You can also be able to tell how amazing this session is going to be. Hello, Ridwan. Please go ahead.
Ah, no, I'm smiling. At the point that I forgot I was even going to this one. So all those big words are there for me. So I was shocked
Absolutely,
actually.
absolutely. You're more than that. You're more than that.
I was,
Thank you
I
for,
was,
for thank you for honoring us again.
ah, okay, yeah, okay. So it's always good to be back here, at least to say one or two things, at least to say one or two things. Hopefully we are able to do justice to what we want to do. Thank you very much for having me again. So, my name is Ridwan, and I I do research at University of Arkansas in Little Rock, and I am currently a suffering and frustrated PhD candidate. Yeah. So, okay, if there's anyone here that wants to do PhD, please don't let Zion tell you any other thing. So, today I want us to, we're going to go through the regression. At first, when I saw the topic, I I wanted I was trying to understand the perspective to actually take. At first, I wanted us to do a deep dive, and then what I mean by a deep dive, right? From my background, a deep dive means let's take one aspect of regression algorithm and then go deep into it. Like, let's understand what the authors of that algorithm, what they wanted to do, and how they were able to do it, and what are the limitations. That's what I thought. But at the same time, I'm like, okay, this is 2025. Not everybody will be interested in that sort of approach because it will be very involved, highly abstract, and then very mathematical, which is something that is not really a good way to introduce a concept to anyone. Like you grab or lose interest very fast if you do not understand abstract concept. Then okay, there should be another approach. Let's look at it from an abridged version. Let's look at a bit of background, something that we all have learned before, maybe from high school, if you went to a good school, or from university, if you went to a bad high school like me, or it was a very terrible university too. then I'm sorry. Then that's the end. It's over. So let's start with that, and then we'll look at how others have built on it. So how deep we're going to go today depends on how much we cover, and then the interest span, and then how energized I have to. But I'll try as much as possible to give you insights into if you actually want to go deeper than what we discussed. So now I'm just going to do a brief intro. I want to launch my notebook so that you can see. Mm, okay. So give me a moment, please. Yeah, thank you. Let me share my screen. Closing all this stuff. Please let me know when you can see my screen. Okay. Great. Okay, so what say regression? What does it actually mean from machine learning perspective? From a very simple from a very simple view, regression is just used to describe a sort of predictive task where your target is continuous. Like it is used to distinguish between another task where your targets are in discrete classes, which you call classification. But if your targets are continuous numerical values, then we say you are dealing with a regression. That's now. This is it in its simplest format. Okay. The most basic form of regression, at least that I know of, is what we call the ordinary least square regression. And this is something you should have done in your high school or in your university days, in math or further math or 101 or 102. Yeah, can you guys confirm you've actually done something like this before, at least with your hand? Can you guys confirm? I need some confirmation that you've done ordinary least square regression before. Oh, okay, let me say, if you done something where you were asked to draw a line of best fits through a set of points. You were asked to draw scatter diagram and then draw a line of best fits. Yeah, okay, yeah, great. So with that regression that you did there, you understand? Yeah, that's what I'm asking if you've done before. You've done before. Okay, great. So we have OLS, which is ordinary least square regression. We have ridge regression, lasso regression. Now, both lasso and but every other regression builds on top of ordinary least square regression. In other sense, you can look at them like they have some cons that's associated with OLS, and we have algorithms that we build to solve those things, to improve on it, like build on top of it and improve on it. So my learning goal for you today is to explain the model, the objective function of each of those algorithms, their assumptions, if we can, and some of the solutions that they prefer to it. Then we can implement some simple from scratch version. Not everything, not with, it's not everything that we can actually implement from scratch. Personally, I've tried to implement support vector regression from scratch a long time ago, and I failed miserably. I haven't tried it again since then. So, the end of it, can actually try and see if you can implement it from scratch. I was trying to implement it from the actual paper, and then yeah, but it wasn't really coming out well. So, but you guys can try it if you want to, as an exercise, just to exercise your brain. You understand that works. Now, let's look at some of the differences. Now, anytime you're looking at any machine learning algorithm, the first thing you need to understand is the objective function, because the objective function is exactly what you want to learn, right? What your objective is, if you look at the objective function of any machine learning algorithm, it's easier for you to understand the scope of the algorithm. In fact, if you want to look for the limitation of the algorithm from the objective function, you can look find the limitation from of the algorithm, right? If you are good with that. Now, for the ordinary least square, it minimizes the mean squared error. Now, what is the mean squared error? It's just, yeah, anytime you look at machine learning things and everybody's just talking about math, it looks at least like it's complicated. It's not very complicated. Mean squared error is just simple. Like you have, let's say you carry out an experiment and you have let's say you are measuring the length of a table. That's your experiment. You measure it 5 times, right? Each time, let's say the actual length of the table is 7 centimeters. But the first time you measured it, you have 7.1, then you have 7.2, 7.3, you have 6.9, 6.5, and everything. Now, what mean squared error is trying to tell you is that the difference between your measured value and the actual value, let's square it. We are going to square it and we are going to divide it by the total number of times that you did the measurement. Now, this way, and then we'll square. By squaring it means what? We are going to punish the model more for any mistake that it makes. You measured it as 6.9 and the actual length is 7 centimeters. The difference is about 0.1, right? Now, that's one. That's, let's say it's minus 0.1. You went, the actual length is 7 centimeters and you measured it at 7.1 centimeters. The difference there is 0.1, right? In order for the model to understand that it is making mistake and to make the mistake uniform, so that you don't confuse the model whether go forward or go backward, minus 0.1 and then 0.1, you take the square. And the square of all real numbers are positives, right? So by taking the square of minus 0.1 and 0.1, you have the same value. So the model looks at the mistake of 6.9 and the mistake of 7.1 as the same thing. Now, by looking at the objective function, that is one thing you can quickly capture as a limitation. If that does not work in your own case, you probably have to adjust this or adjust the penalty. Now, that's why I have to introduce another lesson to you guys. In actual production or in actual production, yeah, production environment, this standard objective function or standard evaluation methods do not always work out of the box. You probably have to tweak it so that it works for the particular purpose and it fits the assumption that you want to do. In some cases, if the model actually did 6.9, right, it's a very terrible thing. And it is more terrible than if the model actually predicts 7.1. In that case, you have to penalize the model more for predicting values that are less than the actual value. Can anyone think of a situation where predicting a value less than the actual value will, or greater than the actual value, where there's going to there are no the let me say they don't have equal importance? Have you ever seen a situation like that before? Anyone? Has anyone ever encountered a situation where predicting below or predicting above do not have equal connotation. They do not have equal importance. So you are predicting the blood pressure of people, right? And the actual blood pressure is a particular value. Which one do you think would take more importance? Predicting a value lower than it or a value higher than it? Which one? Anyone? Eh, Sorry, guys, is my mic working? Can you guys hear me? Oh, okay, great. Does anyone? Which one do you think is more important? Getting a value higher than the actual blood pressure, or getting a value lower than the actual blood pressure? Or do you think they are both important? They are both. Okay. I think both are equally important. Okay. Okay. Right. I agree. I do not agree. Now, why is but because you all okay. That's that's another thing that you all are looking at it from the perspective of the machine learning algorithm is the ultimate judge. The question you should have asked is what is the complete process? The process where the human intervention is the one that is less important. If the value is actually higher, if there's going to be human check, like okay, if I predict higher value, the doctor would have to check the person. Then that is not very important because once you predict the higher one, then the doctor will be there. You understand to check. If the model actually made a mistake by predicting higher, then the doctor will come and check. When he predicts lower and no one checks, then that's the part that we have to punish the model more. So so that's usually so that's or so that's in case of blood pressure. In case of any other thing, maybe yield, CGPA, interest, and all those things, you have to look at the end-to-end process, like what actually happens then, or which of them will give the lowest loss to the company, or which loss can the company actually accommodate. So you don't do these things in isolation. I just wanted to also point that out because I'm very sure after these courses, everybody wants to get a job and you know work and get money and stuff like that. So that's another thing. And also yeah, for interviews too, those things are quite important. So they show you're not just a good person. You understand this and how to apply it to scenarios. Not the machine learning model do not work in isolation. You understand? For some people, 70% accuracy is standard. It's okay for them. Why for some companies they cannot absorb that loss? They have to get to 99% accuracy, even though that looks like that's not possible. But that's it's just you can don't do it in isolation, right? So you have to look at everything end to end. Now let's continue. Now, ridge regression. If I'm not mistaken, I think ridge regression was actually published before. I think the last one was in the 70s. I'm not very sure. Well, okay, let me and can I quickly confirm? Yeah, I think last one was in the give me a moment. I I had a paper somewhere with me. Yeah. So the ridge was in the 70s and Lasso was 1996. Yeah, I get that. So ridge regression now uses something we call L2 regularization. Now, for L2 regularization, this is also a very common question too. You know, it's It attempts to shrink coefficients in the in a linear regression model. I will explain what coefficients is and stuff like that. I just wanted to give you guys a good introduction to this objective function first. It shrinks coefficient, but it keeps all the variables. What we mean is that it drives some coefficient towards zero, but they are not exactly zero. Now, this is a sort of way to do feature importance. Like there are some features that are not very important or that are harming your model. So ridge regression attempts to clamp them down and to reduce their importance. So the model does not consider them very much. Like they did not affect your prediction, right? So, but it performs feature selection, but it's not very good in doing that feature selection because those features still have effects and they can still affect your prediction. As you can see, it has a very similar objective function to ordinary least square. You understand? It has an extra penalty. So this extra penalty is what we call the L2 regularization. Now, lastly, L1 regularization is also similar to um, reach and OLS. Now, for lasso, it actually forces those coefficients to exactly zero. So it totally eliminates those features that are not helping the model. Right? As you can see, it also has the same objective function as OLS, but with an extra penalty, which is what you have here. Now, observe for ridge regression, the L2 penalty uses a squared penalty, like I use a squared difference between the weights. Why this uses absolute value as a difference? Now, please take note of this. This is quite a common question too. What's the difference between L2 regularization and LY regularization? This is not just in linear model. Any model that actually depends on linear model, this regularization are used there. Even in artificial neural network, L1 and L2 regularization are also used as a form of feature control or to control overfitting as well. Please know. Now, for support vector regression, now, yeah, this is the algorithm I said I was trying to implement that it didn't really come away from scratch, so I don't want to do. Now, it essentially uses E2, like an hyperplane, to fit a particular class function on the data, right? For SVR, it ignores small errors and focus on those supportive vectors that are near the boundary of the hyperplane. Is quite robust to outlier because it ignores those small data that are outside of the hyperplane. It just finds a way to what get as much data as it can in the hyperplane. Now, when you use a non-linear kernel in the SVR, they become very powerful, but they are good for small data sets. When your data set, you have a large amount of data set, you can actually fit this model, and it will take a very long time to train, and you might not get good performance as well for support vector. Now, for decision tree, like the way it works is similar to how it works in classification as well. Just uses what trees split the data to minimize variance, right? So it's same approach that you have in classification that you also have in regression. Now, you might tend to use tree-based model when interpretability is very important, right? But there is usually one caveat then for decision tree, which you might not notice at first. It might apply to other tree-based algorithm is that when you use them for regression, they do not do well on data that they've not seen before. Now, then the question will now be for continuous value, how do you know that this data has not been seen before by the model? I'll talk about that when we are down the line. Then ensemble, I'm pretty sure you guys have you've seen that before. So this is just a summary of the key differences between the model, right? And then when and like a quick handbook, a key point to when to use them and how to use them and what they actually do. Now, this is a good shorthand for you to remember the difference model. Now, at this point, let me take a pause, and if you have any question before we go to the next section, I can take some questions. Okay, any question? I think can see one on being raised. Oh, okay, yeah. AI some of food as Louisiana. Can you?
Yes, good evening. I have good evening, everyone. Thank you for the session so far.
Yeah,
I have a
that's
question.
one.
So when you're talking
Okay.
about the model oh God, interpretability. So far me, I know that when I'm using for example now you said for the ensemble methods like XGBoost that it's the interpretability is very low. So like can you explain what you mean by that? Because me, so if I'm using such kind of models and I want to like interpret my results, like to understand how the input features relates to the output. I normally use like sharp. So like
Okay.
I want to understand when you say that the seven methods like the interpretability is very low compared to simpler regression models. Like what do you mean by that? Thank you.
Yeah, thank you for that actually. And you will actually see that, right? Let's say we develop a model to actually predict the yield of crop on the field, or let's say you are the business developer, the business analyst, and you're or you're data analyst or data scientist that build that model, and you want to explain to C-level officers, right? And they're like, okay, what are the features that you used for this model, and how do they contribute to the model? Essentially, can you write a simple equation combining these features together to give us the actual prediction? That's how interpretability for business. Now, when you use Sharp or you use Line or any of the XAI method, you have to even explain the Sharp itself to whoever is listening. They have to interpret the Sharp too, and to understand why Sharp gives a particular interpretation. Then when you use another XAI tool, you might get a different result or a different scale of results. But internally, for each of those linear models, they are just linear combination of the features. So they're quite easy to explain. You know which feature and you know the weight that the model gave each of those features. And then you have a straightforward relative importance of this feature. Easily understandable by you and by non data folks. Now, any other question? Yeah, thank you. Do you have any other question? Okay, yeah, I have another question for you guys. Has anyone taken calculus class before? Maybe calculus one or differential calculus before? If you have not, can you indicate? Exactly. For a tree-based model equation, there's really no equation that directly links those coefficients together. You probably have a tree-based diagram, right? But I think it will better treated on that classification so that you see how the algorithm actually splits the features and then it does it like it's a tree. Like it splits the features and it learns as it goes down the tree. So that's why it can be quite difficult or daunting to interpret. So if you've not taken calculus class before, calculus one or differential calculus before, can you indicate? Okay, okay, what else? Me, okay, okay. All right. Okay, cool. Yeah. Okay, because mm, we need to just leverage a particular method in calculus just to do some very simple thing. So I wanted to know if a larger representative of the class has done one or two things in calculus before. Okay, this is that we are few that we've not done it before. I would also break it down so that you all can also come up to speak to. Now, these are just inputs and everything. The items. I just want to run this. Okay, yeah, I'm just generating some synthetic data that we'll use to fit our model and to do some experiments. No, they are not real data, they're just synthetic, right? So make regression is like is a tool in scikit-learn that you can use to make some regression data on some. That's just what I have here. Now, um, okay, let's jump first. Right. Now, for linear regression model, everyone should be familiar with the equation of a straight line. Uh, can I assume that I have to pick on somebody? I think I want to pick on someone that said they've not done calculus before, so that I can use that person as a threshold of understanding. Can I do that? Or is there someone who wants to volunteer? Do I have a volunteer? Anyone? No, not AI somehow. I want someone out of people that have not done calculus before. So that I can use them as a threshold of understanding so that I can, once they understand, then we can move. Blessing, thank you very much. So blessing, you would have to unmute and then I would, I'll use it as a focus.
Okay.
Now, is everyone used to the equation of a straight line?
Yes, I am.
Yes. So now equation one that we have here, y equals to ms plus k is the equation of a straight line. M here is the coefficient or the gradient of that line. X there is the independent variable. K is the intercept on the y-axis, and y is the dependent variable in this case. Now, when we transform this to a linear regression model in machine learning, we call y the target, x is the variable or feature, and m is the weight that we assign to that particular feature, and c is the bias that in the machine learning model. Now, this is called a one variable linear regression model. If this is the multi-variable linear regression, then you have what? You expand that. So you have a gradient for a feature. You have M1, S1, M2, S2, M3, S3, then to the number of features that you have. Now, this is where the standardization that we were talking about before comes into play. Once you use this, you learn the linear regression model length, you can express the coefficients and the feature using this equation. And it is easier to explain to anyone that, oh, this is how we got the yield of 1 billion tons per year. Because what we fitted this model on the prehistorical data, and these are the weights assigned to each feature. Now, I don't know how much you guys have covered in terms of machine learning, how a machine learning model learns and how it is trained. But we do something we call forward propagation. Now, forward propagation is a way that the model learns. Like we supply a sample of data to the model, it gives a prediction, right? And then we calculate the loss. Loss means what? How far are we from the actual targets? So that's what we do in forward propagation. Now, and how do we do that? We initialize the weight with random. There are different ways of initializing weights, but you can just use random data, right? Since you're going to train the model several times, so you can just start with random data first, just for you to get values in and out. So the weight of the model is first initialized, right? And then we'll feed the data into the model. We can do this in batches because you do not want to it depends on how much data you have and how much memory you have. You can do it in batches and you can do everything at once. It doesn't actually matter if you have small amounts of data. Now, so this feeding the data to the model is done. We multiply the weight of each feature by the corresponding value in the data itself. Now, this is sort of a matrix multiplication. I did not want to bring so many mathematical concepts into this so that we don't get confused, because I know, yeah, if a lot of people are not very familiar with calculus, then definitely a lot of people are not familiar with matrix as well. And I do not want to start doing matrix multiplication. I think I don't this year I don't know if we did mathematics of just some mathematical concept, but I know it was done in the first version of this. I don't know if it was done this year, but let's go. Now we'll look at this too in code and how it works. So once we feed the data, right? We feed the data, we do a matrix multiplication between that data and the weight matrix, then we compute y. Y is our target. Now the y that we compute is the predicted y. We then compare that y with the actual y from our training data, and then we calculate the loss. So yeah, our loss is going to be the mean squared error that I explained earlier, and this is how it looks like in equation. So we take the difference between our targets, our actual targets, and then what we predicted, and we square. Then we sum, and we divide it by the total number of targets that we have. So now, so this was the legend. L is the loss, N is the number of data points, and everything. After we've calculated the loss, we need a way to tell the model that, bro, you are doing fine. Bro, your position is way off target. Now, the way we tell the model is what we call back propagation. Now, forward propagation and back propagation are like standard of training machine learning model. Although there are there is some research now, there is some research into actually training the model with forward propagation only. I don't know how successful they are, but I've seen about 2 to 3 research papers that have proposed a way to actually do just forward propagation. But popularly and for most, as far as I know, forward propagation and backward propagation are still like the standard of training the model. Now, how do we tell the model that it's performing woefully or it's performing bad? So essentially, we are trying to find the local minima of the curve. So the global minima for the curve. So how do we do that? We use partial differentials, and then we use a concept called chain rule. Now, what in lay terms, I think for everybody that has done calculus before, you can be reading this slide. Now, I want to talk to people that have not done calculus before. Chain rule is just now. This is what we want to do. We've calculated the loss, right? But the loss itself, L, if you look at this equation here, L itself is not connected to the weights. What we want to do is to adjust M. We want to adjust M1, M2, M3, and K. But if you notice that in this loss function, M, they don't exist here, right? Only the predicted value, which is the target. And what is the predicted value? Predicted value, maybe it says like 6. That's what we have. L itself is not connected to this. So how do we, from L, go back to the weight and update M1, M2, M3, and up to K? Like, how do you go back and update? So that's where we have to rely on what? On something we call chain rule. Now, what's chain rule? Chain rule means, well, let's combine some intermediate step to get to a particular step. Am I communicating? Blessing, are you following?
Yes, yes, I'm following.
Okay, fantastic. So now let's use a simple concept. Let's say I want to go to let's say I want to go. I'm in Lagos, and then I want to travel to the east of Lagos. I have two alternatives. I can either, like from Lagos, go to Oshodi, then get a bus from there, assuming that I don't have a car. Go to Indo, get a bus from there. Or fly to the north, then to the east. Or go deep to the south and then go to the east. But the most important thing is what I'm going to get to the east. Now, all those are just what the intermediate step, right? We are going to pass through those stages, but to get to our final stage. And there have to be a road that connects where I am now to those intermediate stage, and from those intermediate stage to my final destination. There have to be something that connects them together. Because easily from Lagos, I can get to Ondo State. From Ondo State, I can easily um, I can easily get to Delta, and I can cross the River Niger Bridge into Onitsha, Anambra. Then I can keep going from there. But if I don't get to Delta State, I will not be able to cross the bridge. Right? So those intermediate stages have to be connected. Right? There has to be a connection between where I am now, which is the loss, with the intermediate stage. Then from that intermediate stage, I go to another intermediate stage. I go to as much intermediate stage as possible. I travel from Lagos to Ogun State, to Osun State, to Ekiti State, then to Ondo State. Like all those intermediate stages must be connected for me to get to my destination. Now, and that is exactly what chain rule does. We chain all those intermediate states together until we get to our final destination. And that's what simply you have here. Now, our loss, which is this L, so remember it is dependent on Y. You can see our L here is dependent on this predicted value Y. So we differentiate, so we do the L decay, that means we differentiate L with respect to K, and we get this. Then, excuse me. So after we've gotten those from our loss, the intermediate stages to the final stage, then we calculate the updates for each of the term that we want to update. We calculate the updates for the weight, and we calculate the updates for the constant. So after we do the derivation, I don't want us to go into the calculus, so that we are all together and everything is flowing very well. So the derivative of the loss with respect to the bias term will be this. So forget about this thing that looks like a curvy zero here. Just focus on this, that what this is what we need to update. Minus 2 multiplied by the summation of the difference between the target and the actual predicted value is what we are going to use to update the K, the constant. And this part is what we are going to use to is what we are going to update each of the weight parameters with. Remember, we can have so many features. In linear regression model, the number of feature is equal to the number of weight parameters that you have as well. So that's why you can see SI is multiplied by this, and this is weight I2. So this is what we are going to use to update the weight parameter. Then we do a gradient descent. What a gradient descent is just moving, right? Let's move the K and the weight the towards the direction where we have the minimum amount of loss. That's essentially what gradient descent means. There's a very large amount of research on how to do gradient descent. Very large. But the most popular one is using stochastic gradient descent, right? Probabilistic gradient descent, random gradient descent. Like, let's just move and see if we get the loss. But we don't just jump. We jump with what? With these update parameters. So you can see what we have here is the LDK, and that's what we are using to what? Update the K. Essentially, we are subtracting. But we don't just want to use everything. So we use a percentage of it. And that percentage is what we call the learning rate. You can make your learning rate to be 1, and then it will not adjust the updates to the update. But usually adjust the learning rate so that the model doesn't jump. Because if the model is like a curve, like this. If the model jumps too far, it might miss the global minimum, and you don't want that to happen. So you should let the model move bit by bit, so that it doesn't jump below the lowest point. Sorry, it doesn't jump beneath doesn't jump and miss the lowest point. So that's why we use the learning rates, like how much updates should be applied to the model. So we do the same thing for each of these ways. So we repeat this process multiple iterations until we get the best parameter, until we get the loss, and the loss doesn't change again. Now, everything I just explained there, now that I was just screaming and shouting, in code is not as difficult as it is like in mathematics. So what do we do first? Like this is a class linear regression from scratch. Is it looks a bit uh it's not very optimized, but it works. So you can write a better one, I believe. So what do we do? We initialize the linear regression model with our learning rate, right? And we specify the number of efforts, the number of times we want to train the model. The default is 1,000. It's a good starting point. So we initialize the parameter. Remember, I told you that what the number of features that we have will be equal to the number of weights or weight params that we're going to have to. So that's why we're getting the number of features, which if your x is an array and you get the shape, it's going to be x comma y. So or row versus row comma column. The number of columns is the number of features. So that's why the number of features is the shape and is the second element test. That's if you supply a a two-dimensional data. If it is not, if it's just one feature, then number of features is going to be one. So that's essentially what you're. And I told you that we're going to initialize our parameters with random values. So that's what this NumPy module does. We just select random values to implement that. And our k will start from 0. You can start with a different value, but I just choose to start from 0. Then this is our mean squared error that I showed you earlier. You can see it's all the difference between the predicted value and the actual value, and then we square and we take the average. Now, our updates parameter, the LDY, which is what we have here, minus 2 times this is the same thing you have here. And yeah, the same thing you have here. And for the K2, that's what you have here too. Yep. Then we fit the model. Now, how do we do that? For the number of times that we set as 1,000 as default. Then we take the data in batches. You can take the data at once. I will show you there's another implementation in this notebook where I just use the entire data at once. And then, yeah. But this is just a very lengthy way of looking at it, but it looks at it step by step. So we can fit our model and we can let it train. So currently it is training with the synthetic data that we created earlier. And then we can look at the mean squared error and the mean absolute error. Yeah, so the RMS here is 15.2851, and then the coefficient of regression is 9. Never use this coefficient of regression for anything. It's a very can be quite misleading, especially if you want to do statistical analysis. Yeah, this is the residual and the predicted. So this way. But now let's actually do something else. I want us to do this. Now that lengthy OLS that I showed you earlier can also be written in this form. It's just essentially matrix multiplication and then taking the inverse. Like if you study matrix and you study how to subsystem of linear equation with matrix, right? You just take the inverse of the matrix multiplication, multiply x with the biases which we initialize as ones, take the matrix multiplication, I will be able to get the parameters that are needed. So we use the parameters, we take the matrix multiplication of those parameters and the x value to get our results. So this also, then we can also use the linear regression from scikit-learn and see if we're able to get similar results. So what you have here, this OLS, and then what you have here, are essentially the same. You understand? But this takes everything step by step. You understand? It's not very essential you do everything this way, but this is quite easy to understand, and it's intuitive for anyone who's just starting to learn that. Says non-type. Okay, that's because we we have implemented something called linear regression, so we can just do this. That will not be difficult to do. Yeah. So yeah, the same thing with what we have in SQL, right? So that's essentially what we have in SQL library. So this 15.2021 this mean squared error, and this mean squared error is 15.20. So pretty close. So if we increase the number of iterations for this, we might get better results and maybe do some other optimization as well. But that's just the way this works. And then do you do you all have any question before we proceed? Any question? Yeah, I know these are very, very simple models. I know. And it's um
A simple
everything is
question.
pretty advanced.
I have a question.
One question. Yeah.
Yes. Um. Well, in as well as the theoretical parts, right, that you explained is more understandable. The code seems really complex.
Really?
Yeah. Is there a reason why we are bringing in matrices multiplication? Oh, yeah, yeah, yeah. I understand why, but
The first version or the second version?
the first one.
Uh it's are you talking about this or
No.
or this?
Oh, oh, okay. No, the
Oh,
first one. Even the second one too.
yeah, in the second one we did everything like how I explained
From
it. Right. We initialize the parameters which we've done. So to get the weight, and then we can see what we have here is dot product, like multiplication.
yes,
Like remember,
product.
remember the equation says m times x. So that's essentially what we have here.
Yeah. I
So
think it's the
over
self
here we are.
extend the self
Yeah,
the
over here is
self
where
self
oh okay, self. Is it this self?
yeah, all of the self. I think it makes it, but I guess I'll go through it
Oh,
again.
okay. The self are not part of the code. The self is just it's a way for Python classes to refer to itself. So it's not compulsory we use self, I could use something else. But you can see here, this starts with itself. It's a Python paradigm. Now, okay, so you see this linear regression now. You see get loss, update parameters, right? As long as I'm within this class, I can call any of these functions. You can see, look at this one that we did here. This is where we initialize our learning rates, right? LR.
Yeah.
But here, we
Mhm.
are calling this here. If we do not initialize this with self, we will not be able to access it from this method.
Okay.
Okay, so that's why
Mhm.
this self is so these are actually class method, right? It's a topic on its own, like in Python programming, like object oriented programming. So yeah, so I think I can just go through that. So the self there is just forget about the self, just a way for this class to refer to itself. All this so that we can reach each of these methods from inside of the class itself. So I can use something else apart from this, but that's just the it's just Python standard. If I use something else, as long as I'm consistent also, it will still work. So it's just Python
Yes.
standard.
Thank you.
Yeah, you're welcome. Oh yeah, of course. We could have done this without creating a class. Just that we have to define a lot of things. Because we could have created each of these functions one after the other, like create the get loss. If I do get loss, you don't even need it. You just mean square error, right? You have it already. update parameters, we just update the parameters. We can do this in that class, but this is just the proper way to organize everything together. Yeah. Yeah, there is an argument that's going on currently in the programming community about not using object-oriented programming to do anything. Yeah, like it is, it can be complicated or it can be deep. Um, that is due to a lot of abstractions, encapsulation, and inheritance. Like you just want to change one single thing, you have several inheritance. You have to go from one class to the other, to the other, to the other, to actually understand what I'm missing. Yeah, it's just programming syntax and guidelines. But yeah, but we can do it without that. But is it a proper way for you to manage your model is to use OOP to do that. Any other question? Okay, we are all good, right? So we can proceed. So don't worry, this is the last time we're doing anything from scratch. Every other every other one we just be using the model. We just use the one I've implemented before. It's scikit-learn. Scikit-learn is like it's like the machine. Oh, okay. I said we're not doing anything from scratch again. I'm sorry. Let's do this one from scratch. Now, remember what I said about ridge regression, right? It's just this is the objective function of linear model, and we add the penalty to it, right? So this that we implemented here, the first one, this what we have here, and we add a penalty to it, and that's what you have here. So we can also use ridge from scikit-learn now. So this is ridge from scikit-learn. We can just import it. So alpha is the parameter that controls the penalty, that controls how much penalty you actually apply. Like how much of the parameters, how much of the coefficients do you want to move towards zero, right? So for most times, at least I think during the days of competition with which we usually try this in hours of 10. So you start with 10 is past zero, which is one, no, 10, 100, and the likes. And you can go below two. You can go 10 raised to power minus 1, that's 0.1, 0.001, and stuff like that. So that's usually how we do. I don't know why that is. I think it's just something we saw others do, and it kind of becomes an habit. So it's usually powers of 10 that we use. Now for lasso, same thing too. For lasso, so same thing. We just introduce what we introduce the penalty, right? So this time around, we have to move them from permanently to zero. So we can also implement that. Yeah, and for some reason, yeah, the last one I implemented from scratch has a better performance than scikit-learn. I don't know why that is. I have to go through it. I saw it yesterday when I wrote this from scratch. I don't know if there's data leakage or something like that, or if it's actually better than it. I don't know. I would have to check scikit-learn implementation and see just my and see if there's any difference between this and that, and then yeah, because the difference is quite much. The RMS is quite much, so I need to know what exactly is going on there. But don't worry about that. Now for support vector regression, right, we can just use directly from scikit-learn, which is what we have here. And you can see the RMSE is poorer than that. I'm not saying this is the final result. I'm not saying SGL is worse than that. You can do some hyperparameter tuning to actually see if it gets better user. Here we are using the RPF kernel. So you can use the poly kernel or linear kernel and see if you get better results. Right? And this is just for demonstration purposes only. Then for decision tree, same thing. We can use that. If we try to implement decision tree from scratch for regression, I think we'll be here. We'll be here to the end of the day, actually, to actually understand what's going on there. It can be quite involved as well. Let's do a simple experiment to see how the mass depth can actually affect the mass depth here. Can you can see it as the number of trees that's been no, I won't say the number of trees. I'll say the depth of each tree that's been built. So if you want to see more about this experiment, you can click on this link. It will take you to the scikit-learn page, but that's where I got this information from. So let's make simple random data sets. Then let's fit two regression model on it. First, the maximum depth is 2, and then a maximum depth of 5. And let's see how it performs. Now, if you see that, you see this, the model with the maximum depth of 2, right, has a poor approximation of the data. For some reason, what it predicted for this data point is at this point, which is far off from it. Then you can see that the mass depth of 5 has a closer approximation to the data than the model with mass depth of 2. Can we all see that? Or do you have a different opinion? Is it overfitting? We can't really say. For you to say something is overfitting, you have to look at the train and test. Overfitting is when a model performs very well on trained data, but it performs woefully on the test data, on sim data. Mm. For everything we are seeing here is just the test data. So, okay. Now, this is for a model with a single feature, right? Let's look at the model with multiple features. So data with multiple features. So the same way we create random data with multiple features, then we fit three models, mass depth 2, mass depth 5, and mass depth 8 to the model. Then let's run that. Now we're looking at this which model has a very good performance. Okay, vote. Everybody must say something here. We're looking at it. Then we'll show the results. Everyone was taking votes. Looking at it. I've not seen anything in the chat. Mass depth 2. Okay. Everyone, we need to print the results. But everyone dropped their results. Let's see. I've only seen one. I've only seen one mass depth 2. Every other person, which model there do you think would have the best performance or is hitting the data more? It's 2 8. Okay, let's look at it very well. Let's look at it for like 2 or 3 minutes. Okay. It's too good to be true. It looks perfect. Okay. Let's look at AIDS. Hmm. Yeah, AIDS is very good. I think it has the best performance here. Is it? It doesn't look good to be true. Then we'll have to verify and see. But since this is random data, yeah. But from looking at this plot, it seems to have the best performance. Then for ensembles, bagging, random forest, gradient boosting, they operate by combining simple or weak learners to to reduce the variance or reduce variance or bias. The main aim is to combine those weak learners to give a strong performance. So you have random forest that combines a lot of decision trees together. Then you have gradient boosted tree, you have gradient boosted machine, you have a strong boosting algorithm, you have light GBM and the rest of them. So, but scikit-learn has gradient boosting regressor, and it also has the random forest regressor. For XGBoost and light GBM, easily you can install them from PIP and you can test them out yourself. Now, okay, let's just do a simple classification. Just how it looks like. So from here, the decision tree has the highest RMSC, right? And you can see that the linear models have the best RMSC that we have. So there's something else I wanted to mention earlier that I spoke about random forest or tree-based model not being sometimes very good because they tend to perform quietly in data that I've not seen before. It's just from practice and from my experience. Now, this is how it is. Let's say you have historical data of prices between 2000 and then 2025, and you want to predict future prices. The best way to do this is to split your data into past and future. You can split your data from 2000 to 2017 and use that to train the model and see how the model performs from 2018 to 2025. That's the best way to split that because if you don't, there might be data leakage. Because if you train your model on data like randomly, then you're already leaking some information from the future into your data. Now this is the thing now. If you use a decision tree or random forest to train a model from 2000 to 2017, and you want to predict from 2018 to 2025, it might give you garbage. In fact, if the highest value from 2017 was like, let's say $5,000, it might start predicting $5,000 for 2018, 2019, 20. It might start predicting the same constant value because that is the only thing that it has seen. It has not seen any year that is above 2017 before. That because of the way decision tree works. They work by splitting, right? So because I've never seen something like 2018 before, something in that range, the highest I've seen before is 2017. For years that are way, maybe 2020, 2021, it might just start predicting the last value that it saw. That's something I've seen in process before. So you may want to be very careful with that. And usually when people say, oh, it didn't happen to them, then I realize that they're trained on random data. And there is data leakage. If you do not train on random data and you arrange your data in that way, you might have that issue. You guys can try and confirm it too and see if you're able to reproduce it too. It was not something I saw in the past, like maybe a year or 2 years ago. I just wanted to share that with you in case you are also doing that. Because as a good machine learning engineer, always know that you need to know the limits of your algorithm so that when you're training the model and you get some metric, you'll not just be happy that your model is performing very well. You know, yeah. So when you apply shuffle, you randomize it. You understand? If you randomize it, it means what there might be leakage too. But you can random after splitting token and test, you can randomize it. No problem. But if you randomize it before you split the training and test, you might have some feature data in the training data, right? Again, I'm not this is not oh this is not holy grail, this is not set in stone. Right? You guys can also experiment it out. It's not something I experienced a year, I think about 2 years ago or so, right? And then and when took people to actually do that to like experiment and they were not getting that, then I realized that they were actually randomizing their data and such they were data leakage. So it's really very good when you understand that, oh, this is the limitation of your model. If you are getting some results that's very good, you should be suspicious about it. That's what will differentiate you. That's what differentiates you from every other person that they attend this course. You need to be very skeptical about your results. It's better you detect the error before somebody else detects the error for you. You understand? So, and then don't be worried if you get a very poor performance. It happens all the time as first, you know. So don't just be happy that oh my the error is very low. Oh, we have 8 accuracy. No, you need to understand. Okay, this accuracy I'm saying is it the right accuracy or it's just fluke or it's just because of random data, right? It's just because of random data. Or is it just because of the way maybe I split my data in such a way that it's not balanced and then most of the test data there's something like there are similar things in the training data too. So you need to understand that that's why it's good we look at this thing from scratch. Understand how they're going to work, understand their assumptions, and understand where they might not work. You understand? So I think if you have any question now, you can ask me so that we can iron it out. But that's the end of my presentation. This is the time for you to ask your question. Okay, everyone is quiet, and I assume there's no question. Oh, is that don't use tree model for time-based program? I will not say that, and I will not say. I will say yes or no. I will say you test it yourself first, because the one I described now, guys. See, that's what you need to understand. This thing is there's the art and the science part of it. What I explain now, you have a simple feature, and that feature is here, right? And the model has not seen the feature extend beyond 2017. Now, let's say we had like 5 features. It might not matter because those other features might be continuous. And then the model might have seen that range before and it won't have any problem when you're testing in production. But because when I just described now, it's just one feature and the feature is here. And the maximum that the model has seen before is 2017. So when you see something that's above 2017, it doesn't know what to do. But in the case when you have 5, 10 features, right, and those features are continuous, it might be easy for the model to find a shortcut around others and not use the one that it hasn't seen before and still give you a good performance. You can test it out. But always ensure that when you have a time-based problem like that, and it has to do with predicting the future, and there's a date involved, try and split along the dates and see. Except if it doesn't matter. Yeah, it's about trying different algorithms to see the one that works. Yeah. Is it possible to see a data set I know which algorithm? This is there's no science to that, but there's an art. There's a science part and there's art to it. For example, if I give you a time series problem, such as stock prediction stock prediction or weather forecast or something like that. You want to use a model that understands sequence. And so if you're using a linear model, or now you don't want to, you might not use this square regression model. You might use ARIMA model or SARIMA or something like that. Something that has a moving average that can help you, that can help you make sense of the data that you have into like a good approximation. Or you start, or you have a lot of data, then you want to use a sequence-based neural network. Maybe you start using RNN, LSTM, or the different variants of RNN, right? So now that's the art part. So from experience, you tend to know, okay, this particular problem might be this particular algorithm is better suitable for this particular task. You understand? But you don't just but there are some tasks where okay, if I have a classification task now, I'm fine. I can just stack all the classification algorithms that I know and start trying the one after the other and see the one that gives me the best results. But if you are stuck classification algorithm to do a regression task, then you know I'm joking. Or if we have a stock, let's say a task like stock price prediction, and I stack three based algorithm like decision tree, right? You might think I'm joking too. But if I use something like maybe a gradient boosted tree like SG boost or something like that, you might be surprised to get a good result because what you have a lot if you have a lot of features, those models might actually be very good um in aggregating those features together and giving you a very good result. Yeah. So there's the science part to it and there's the art part to it. So the art part is not taught, it's learned by experience. You just have to try it out. But ensure that you're not disobeying science when you're trying the art. You understand? So you have to be ensured that, oh, what I'm doing, the objective function of this is good for the task I'm doing. I'm not using classification for regression. I'm not using regression for classification. And there's no data leakage. And I'm using the right metric to quantify my results. So don't disobey science, but ensure that you are creative with what you're doing. So there's the art part. You can only learn that by experience, or from others' experience. Maybe checking what others have done before, the code and everything. Yeah. Yeah. Oh, another thing is expert knowledge. That is very, very important in data science. Expert knowledge is very important. So there are some things that do not make sense in some field. For example, you cannot have a CGPA of zero. That is impossible. So expert knowledge will tell you that okay, if you have missing data in results, and that missing data is a GPA, you cannot put zero there. If you put zero there, then you are joking. So that's expert knowledge. Or some accounts. The time Nigerian banks do not allow you to have zero naira in your account. So if you have missing values, you cannot put zero there. Expert knowledge. Yeah, checking for multicollinearity is a very good. We did not cover explorative data analysis here. Probably have covered multicollinearity. It might be good to check for that, but those very complex models that are not linear models, they do not care about multicollinearity. They actually they do it internally themselves. They do a sort of feature importance themselves. I just use the feature that gives the best prediction. That is, it's a two-way blade. In other sense, the model can actually look at a single feature and say, that, oh, this single feature is very good for predicting this particular target. And ignore every other feature and just use that feature only for prediction. So, that internal, so the model can do that internally. For example, if you use Lasso and Ridge, they might do that internally, right, by cutting out some of those features, reduce them zero because they do not contribute and focus on other features. Decision tree-based model also do that too. They have a way of using the feature that gives the best variance, or yeah, that's able to capture the targets more. So multi-analysis will be very big thing 10 years ago, but now it's just important for you to discover it in the project analysis. Because for most algorithms that you probably would build, you might, yeah, it might not really matter very much. I'm not saying it doesn't matter, but I know it. Yuri, any other question? I want to add a bit. What do you advise as I'm looking to use or try out everything? You know, start from linear models and go to non-linear models. Try out everything. Try everything, like experiment. Get data, practice and practice and practice and practice. You cannot over practice. Practice. The more you practice, the more you know. Practice, practice, practice. You practice, maybe you're not sure of your results or you know. Yeah, oh, another important thing. Because it might be very difficult for you to get mentorship or to get someone to check your work, right? So one good thing you can do is look for indirect ways of getting people to check your work, right? Do not go on LinkedIn and say, oh, I just learned last week's regression, and this is my prediction, and this, that, that. But people just tell you, oh, good work, and this, it doesn't really work. Instead, look for people, like real people that you can mail, to help you check your work. Do not boggle people, right? If you have someone today, maybe you don't have them for the next 2 months, look for somebody else to help you check your work. Some people might be very interested in seeing your progress, but remember, they also have things that they are doing. And also, as you are learning, you have to take it easy and be very humble. You understand? Humility is very important in this space because that thing that you know today, some people already knew it 50 years ago. So you take it gradually, you learn, you learn from others, see what others have done. Some people post that online, some people that stocks online, you listen to what they do, how they do it, learn some things. And I can remember I won a competition before because I saw the way somebody processed some missing data somewhere, like that was the first time I ever did it. Usually we feel missing data, but the person said, why would we feel missing data? Why don't we just make that particular feature a target and use a machine learning model to train on every other data and use to predict for the missing data? Yeah, and I was like, oh, this is nice. This is nice, right? So I trained it and I got money. And I bought one laptop that year, Get so you can learn from others too. Yes, yes. So this person was saying is, but I want to position, and just one laptop that is so that somebody can learn. Because laptop we're using, seeing ordinary linear model to be hot. So that's the laptop. You understand? So you just have to see what others have done, learn from them indirectly, right? Because it's very difficult. Like let's say everybody here sends me email. I probably will not respond. I will respond. It might take time, or I might take one or two or something like that. So that's the way I see you can do this, right? Learn. Look at this. Because you guys are just starting now, you are very lucky because you have a wealth of knowledge that other people have done before. That I'm very sure you cannot finish consuming it before you. If you don't have a job now, before you get your first job, you cannot finish consuming. You cannot even do 10% of what has been done. You understand? Because by the time you see notebooks that others have done, and see the amount of things there, before you even understand it, there's a job, the job market is already calling. So it takes time, build and build and build. All this I'm saying, I'm not saying it because I read it yesterday. I'm saying it because I've learned it and I practiced some years back. So it takes time to build those things. I'm not saying it will take you years to build yours. No, it might take you weeks or months for you to get up to this stage, because now you are here. This program was not available then. When it's available now, so she can live faster. Yeah. So, in the absence of any other question, I think we can. In production, we do rather improve model algorithm. Oh, this one, it depends. Everything, it depends in this industry. Sometimes you see that your um you have to, when you deploy your model, you monitor your model in production. Yes, sometimes there can be data drift. That means this data is way different than what your model was trained on. and then you have to probably retrain the model. When you retrain the model and you see performance gain in the model, that's good. But when you not see performance gain in the model anymore, you might have to change your architecture. Or somebody says that there's a better architecture for this model. Why are you still using this architecture that was published 5 days ago? There's another one that was published today. You have to try it out because you don't want to lose your job and see if it gives you a better performance. That's why there are benchmark. There are some data out there that are benchmark that you used to say, okay, my model that I trained today has a performance on this. This model that somebody published just 5 minutes ago, let's benchmark it and see, oh, it's better than our model. Okay, let's move. So sometimes you have to return your model. You cannot, data is very expensive to get. To get data and label data is quite expensive, right? And if you're in a good place, your model probably gets retrained with new data every, like, maybe the frequency that is determined by your company. So sometimes you have to change the model algorithm, the model architecture to use better ones. Or sometimes you just have to improve your data. I'll give an example. Given a model one time, in instance, was an NER model. The model had one problem: dates. The failures of record document was it to train that model. But what if I tell you that there are some date version? You know, there are so many ways of writing data all over the world. There are about 4 different dates version, popular one, that are not present in the millions of data that was used to train that model. So the model had plenty issues with anytime it gets those dates. When that model is in that part of the world, it suffers from that. So easily, instead of retraining the model in the entire data, we just introduce that data into the data by converting some of those dates in those documents into the new version. And the model started working very well. So it's like there's a science part to it and there's arts part to it. And training model is very expensive too. Like big ones is very expensive. So, all those things are in company decision, but you have to analyze, is this a model problem or a data problem? So that's what will guide you in your decision. And yeah, the company can say we don't have money to train a model. That performance that you saw that has been done somewhere, let it remain there. In this company, they are good with 50%. Anything you want to do, you can do. We don't have money to train a model. What will you do? You say no. You swore in your life that you always working with state of the art and you don't want to train it by force. You have to leave the model the way it is. Yeah, so it's you analyze, then you present, and organization make decisions. Okay. Uh, there's no other question. I'm going to hand it over to Samuel.
Oh yeah. Hi everyone.
Hi.
All right. Thank you very much for that amazing one. It's been very, very insightful. I believe there are no more questions. Okay, so yes, there are no more questions. All right, so this has been a very exciting session, and as we rightly mentioned from the beginning, Ridwan is a family to the AI Summer of Code, right? He was here in the past edition, and he's here also. And from the interactions, I can tell already that this has been an even more than wonderful session. So yes, thank you very much, Ridwan. On behalf of the AI Summer of Code team, I'd like to say a very, very big thank you for the insights that you have shared, for carrying the participants along and helping them through this particular deep dive session. I believe for everyone, this has been more than a deep dive session, right? We can't wait to see what the participants will do with this. We're looking forward to all of that. Please connect with Ridwan on LinkedIn. His name is Ridwan Amure. I think I'll just get the link and share real quick. Right, but yes, everyone, please connect with him on LinkedIn. So I'll have that shared on the WhatsApp group, right? But yes, thank you very much, Ridwan, once again on behalf of the AI Summer of Code. I'm sure the participants have had lots and lots of knowledge and insights to take from this particular session. I can see Dr. Z clapping already. I'm sure he's having a well fulfilled day already. So thank you very much once again. Was so excited and grateful to have you here at the AI Summer of Code, and we'll definitely keep your picture in the AISOC Hall of Fame. Right, it's a very good one, so we'll definitely keep it in the AISOC Hall of Fame. Thank you very much once again. Do have an amazing day. Bye.
Thank you, everyone. Have a nice evening.
All right.